Hey, Jalen.
Guess what?
What?
Can you help me with Chapter 9 Chemistry?
Yeah, of course.
Does right now work?
Right now it's fine.
Can you come over?
Okay.
Sweet. See you soon.
Alright, see you soon. Bye. Hi, Jalen. So, Jalen, what do you need help with?
Pretty much everything. I don't understand this dang chapter in chemistry.
Okay, well, Chapter 9 is about acids, bases, and salts, which are among the most common and important solutes found in solutions.
What does the Arrhenius say?
Well, Jalen, pay attention. In 1887, Svante Arrhenius proposed a theory dealing with electrolyte dissociation. He defined an acid as any substance that provides hydrogen ions when dissolved in water. He also defined a base as any substance that provides OH ions when dissolved in water.
Alright, Miss Smarty Pants. I got a crazy one for you. What's the Bronsted theory?
In 1923, Johann Bronsted and Thomas Lowry proposed an acid-base theory about the behavior of hydrogen. They defined an acid as any hydrogen-containing substance that donates a proton to another substance, and defined a base as any substance that is capable of accepting a proton from another substance. From there, a conjugate base is the species remaining when a Bronsted acid donates a proton. Every Bronsted acid and the base formed when it donates a proton is a conjugate acid-base pair. In the top equation, HNO2 behaves as a Bronsted acid by donating a proton to H2O, a base, in the forward reaction. In the reverse reaction, H3O, the conjugate acid of H2O, donates a proton to NO2, a conjugate base of HNO2.
How do you name acids?
Jalen, this is how you name an acid. The word hydrogen in the anhydrous compound name is dropped. The prefix hydro is attached to the stem of the name of the nonmetal that is combined with hydrogen. The suffix IDE on the stem of the name of the nonmetal that is combined with hydrogen is replaced with the suffix IC. The word acid is added to the end of the name as a separate word. So what would HCl be, Jalen?
HCl would be hydrochloric acid.
Correct.
Yeah!
But remember, there are different rules when hydrogen is covalently bonded to a polyatomic ion. All hydrogens that are written as the first part of the formula of an acid are removed. The polyatomic ion is left over. When the remaining polyatomic ion has an ame ending in the suffix ATE, the suffix is replaced by IC. Or, when it has a name ending in the suffix ITE, the suffix is replaced by the suffix OUS. The word acid is added. If a polyatomic ion contains sulfur or phosphorus, they are expanded for pronunciation reasons to sulfur or phosphor before IC or OUS suffixes are added. You know the rules. What is H2CO3?
H2CO3, I think, would be carbonic acid?
You are correct.
Sweet, I'm finally getting it. What's pH?
Well, pH is defined as the negative logarithm of the molar concentration of H in a solution.
So pH equals negative log H plus, or H plus equals 1 times 10 to the negative pH? So what are all these solutions?
Well, there's only 3 types of solutions: neutral, acidic, and basic. A neutral solution is any water solution in which the concentration of H3O and OH are equal, with the pH equaling 7.
And here's an example of a neutral solution: purified water.
There is a solution in which the concentration of H3 ions is greater than the concentration of OH. The pH is less than 7, and that is acidic solution.
Now I'm going to show you some examples of acidic solutions. milk, lemon juice, dish soap, carbonated drinks, pickles, mayonnaise, vinegar, and aspirin.
Then there's a basic solution in which the concentration of OH is greater than the concentration of H3O. The pH is greater than 7.
Now there's some examples of basic solutions. Detergent, toilet bowl cleaner, baking soda, and Windex.
Than 7.
Can I try a problem?
Yes, okay. So you need to classify which solution is basic, acidic, or neutral.
Plus equals 1.0 times 10 to the negative fourth moles per liter. So now I have to configure OH negative's molar composition. OH negative equals 1.0 times 10 to the negative 14th moles per liter squared divided by 1.0 times 10 to the negative fourth moles per liter, equaling 1.0 times 1.0 times 10 to the negative 10th moles per liter. Being so, H3O plus equals 1.0 times 10 to the negative fourth moles per liter, and OH negative equals 1.0 times 10 to the negative 10th moles per liter. So therefore the solution is acidic because the H3O plus is greater than the OH negative.
That's correct. So Jalen, do you know what the strengths of the acids and bases are?
I think so.
Okay, tell me.
Well, when salts dissolve in water, they generally dissociate completely. But this is not true for all acids and bases. The acids and bases that do not dissociate almost completely are classified as strong acids and strong bases. Those that dissociate to a much smaller extent are called weak or moderately weak, depending on the degree of the dissociation. The strength of acids and bases is shown quantitatively by the value of the equilibrium constant for the dissociation reaction in water solutions.
It's good. Here are some common strong and weak acids. Hydrochloric acid, nitric acid, and sulfuric acid are examples of strong acids, while phosphoric acid and sulfurous acid are moderately weak. And nitrous acid, carbonic acid, and acetic acid are considered to be weak acids.
Alright class, time to take your Chapter 9 test. Take out a pencil, paper, and a calculator. Let's go. Thank you, Jalen. I'll grade it right now. Emily, could you hand these papers back?
Sure.
Yes, I got an A. Yes!
Choose your destiny. Flawless victory. Choose your destiny. Flawless victory.
Okay, it's recording. It's recording.
Fight!